Hello everyone, how are you? Fine. Today we are going to discuss Green's function and its application in scattering theory. This lecture is in connection with our earlier lecture on scattering theory and its wave mechanical picture. Green's function is a mathematical function, and we are going to see the Green's function in mathematical point of view. In mathematics, Green's function is the impulse response of an inhomogeneous linear differential operator defined on a domain with specified initial conditions or boundary conditions. This means that if capital L is the linear differential operator, then the Green's function capital G is the solution of equation LG equal to delta, where delta is the Dirac's delta function. The solution of initial value problem Ly equal to f is a convolution of G star f, where G is the Green's function. This is the definition from mathematics point of view. Now we come to the statistical and scattering point of view application. Green's function application in scattering theory. Schrodinger wave equation is a differential equation. It is possible to obtain solution of scattering amplitude by transforming it into an integral equation. This choice is done by the help of Green's function. We know very well that Schrodinger equation is a differential equation. In a scattering problem, we have to convert it into an integral equation. And that is done with the help of Green's function. So in a block diagram, it is simply mentioned that the Schrodinger differential equation using Green's function converted into integral equation. So this is a very simple application of Green's function in scattering theory, where the Schrodinger equation is converted into integral equation. Now let us define that let omega be any linear differential operator defined as operator omega x del. This is a linear differential operator. So we define that operator omega can be written as C C1 U1 plus C2 U2 equal to C operator omega U1 C2 operator omega U2, and where U1 and U2 are arbitrary functions and C1 and C2 are constants. Now let us come to the next slide. Now let us see that any function g x prime is defined in such a way that operator omega x del g x prime equal to delta x minus x prime. And this is defined as per the mathematical Green's function theory. And this is said to be a Green's function for operator omega. So the way in which a Green's function is defined by using linear operator omega is depicted in this equation. If any solution capital S of the homologous equation, which is omega S equal to 0, right hand side is 0, so it is homologous equation, to a particular Green's function capital G, the result G plus S is still a Green's function. So it is written as operator omega G plus S is equal to delta x minus x prime. And this is called as equation number 3. Conversely or reversely, the difference between any two Green's function is a solution of homologous equation. And the general solution of any inhomogeneous equation is operator omega x del ux is equal to fx. And that is named as equation number 4. And it is inhomogeneous equation because right hand side is not equal to 0. This can be converted into Green's function by expanding fx, that is on the right hand side, as a linear combination of delta functions, means simple multiplication. So fx is equal to integral delta x minus x prime f x prime d2 prime, and primes are shown as the dummy variables. Dummy variables have no importance whenever we put the limit in the integral. So in mathematics, many times dummy variables are used and those are represented as prime. Now let us come to the next slide. Now if u0x is any function such that operator omega u0x is equal to 0, let us call it as equation number 6. Writing for ux, so ux is equal to u0x plus integral gxx prime fx prime do prime. That is equation number 7. Now, we are rewriting equation number 4 that we have already written earlier. So, operator omega x del ux is equal to fx. Now, using 7 in equation number 4. So, equation number 4 we have already written. So, that operator omega x del. Now, we are putting the equation number 7. So, u0x plus g integral x x prime f x x prime d2 prime bracket over e is equal to fx. Now using our equation number 6, because we know that in the above equation number 6 is given, operator omega u0 x is equal to 0. So first term becomes 0. So it is integral omega x del g x x prime f x prime d2 prime is equal to fx. Now using equation number 2, so it is integral delta x minus x prime f x prime d2 prime is equal to fx. And this is equation number 5. This is the same as equation number 5 mentioned earlier because we are not naming it as another equation or a different equation. It is nothing but equation number 5 which we have obtained earlier. This is the solution of equation number 4. And to obtain a particular solution, one has to make a specific choice of Green's function, g, and the function u0x in equation number 7. So we have to make a choice of a Green's function. Now we come to the Schrodinger equation, which is written in a box. Now Schrodinger equation is written as h cut square divided by 2m del square ux in bracket e minus vx ux equal to 0. That is the standard form of Schrodinger equation. Now we multiply the whole equation by 2m divided by h cut square. So first term will be operator del square ux. Next term 2m divided by h cut square e minus vx into ux equal to 0. Now we open the brackets. So del square ux plus 2me divided by h cut square ux minus 2mvx divided by h cut square ux is equal to 0. We call it as equation number 8. Now we are focusing on equation number 8 and we are converting into a box. Now in this box, we are writing for equation number 8. So 2me divided by h cut square is equal to k square. And 2mvx divided by h cut square is equal to capital Ux. We call it as equation number 9. Now, using equation number 9, in equation number 8, we can convert it into this form, which is highlighted by blue. So, del square plus k square Ux is equal to capital Ux into small ux. And we'll call it as equation number 10. Equation number 10 has a form similar to equation number 4, where considering that operator omega is nothing but equal to del square plus k square, and fx is nothing but equal to capital Ux into small ux, and which is highlighted by the yellow box. So it is highlighted by yellow box, and we call it as equation number 11. The Green's function for equation number 10, which is highlighted by the blue box, can be deduced from the well-known fact. This is the well-known fact for the delta function. So del square multiplied by 1 upon r is equal to minus 4 pi delta x, and that is equation number 12. So using equation number 12 in equation number 10, and also writing for ux, it is again, we have already earlier derived that e to the power plus or minus ik r by r is represented for ux. So operator can be represented as del square plus k square plus or minus e to the power ikr divided by r is equal to minus 4 pi delta x, and that is equation number 13. Now let me come to the next slide. Now replacing the following things in equation 13 and rewriting the Green's function for g plus g and minus g. Now, we writing for x is x is equal to x modulus x minus x prime, and r is represented for x. So we are writing that operator del square plus k square is equal to g x x prime delta x minus x. And wherever r was there, now we are representing by modulus x minus x prime. So it is e to the power plus or minus I x modulus x minus x prime and divided by modulus x minus x prime. And it is equal to minus 4 pi delta x minus x. Now, this equation can be further written in form of this equation, that operator del square plus k square is equal to minus 4 pi, because 4 pi we are taken into the left hand side, e to the power plus or minus modulus x minus x prime divided by modulus x minus x prime is equal to delta x minus x prime. And this is similar to the equation, because here we assume that r is equal to modulus x minus x prime, and this x is equal to simple x minus x prime, and that modification we have assumed over here, which is represented by this yellow box, and this is again used in equation number 15. Now, equation number 15 is compared with equation number 14, and we can find out that g plus or minus x prime is equal to exponential e to the power plus or minus I a x minus x prime modulus divided by minus 4 pi modulus x minus x prime. And this equation can be compared with equation 13 also on the previous slide. And keeping in view with equation number 7, equation number 11, equation number 16, the solution of Schrodinger equation is written, and this is written for the integral equation for ux. So ux can be written as e to the power ikz minus 1 upon 4 pi integral e to the power plus or minus ik modulus x minus x prime divided by x minus x prime modulus ux prime small ux prime d2 prime, and we have used here prime variables as dummy variables, and that is highlighted. This is in connection with the wave mechanical picture, because at infinitely large distance we are getting the two type of wave. One is incoming plane wave and another is a scattered wave. Now, scattered wave is represented in form of an integral, and that is equation number 17. Now, one can see that in this equation the potential function is a factor in equation number 17. And we consider that value of x, and that is the potential function Vx prime, is very small and do not contribute to the integral. So we have taken an integral over the complete range, but for the value of V prime x or Vx prime is very high only near the value of origin. At other places, the value of Vx prime is very small. So Vx prime is very high value near the origin, and which in fact contributes to the integral. At other region, value of Vx prime is very small, and that is why it does not contribute to the integral. So coming to that particular fact, we have represented this in a vectorial diagram. This is a vectorial diagram, and this is the x, this is x minus x prime, this is vector x prime. So vector x prime and vector x. The difference between the two vector is represented by x minus x prime, and we are taking a projection of x prime on the vector x, and that is represented by x prime dot x divided by r. Now focus on this equation number 18, which is shown in a box. And whatever we have mentioned over here in this writing, it is represented over here, because modulus x is approximately equal to r, where r tends to infinity, because the x is very large and that is shown with very large magnitude vector. So it is modulus x tending towards or approximately equal to r, where r tends to infinity. And second assumption we have made that modulus x is very, very greater than modulus x prime. And naturally, we can see in the vector diagram, modulus x prime, the magnitude of vector x prime is very small with comparison to modulus x or magnitude of vector x. And in that case, we can convert x minus x prime is approximately equal to r, because r and x are equal to each other from this particular thing, and minus x prime dot x by r. And that is represented in vectorial diagram, that x prime dot x divided by r. Now r is as it is, because we have shown over here, r is as it is, and that is represented, x by r is represented as unit vector k. So r as it is minus x prime dot unit vector k, and that is represented by equation number 18. So we are going to modify in equation number 17 the Green's function, where we have written exponentially to the power I k modulus x minus x prime can be represented by r minus x prime dot k, and that is represented in equation number 18. And the scattered particles observed at x have a momentum k in the direction of x, so that unit vector is taken as k x by r, and that is what we have used in vectorial diagram. The term x prime k in equation number 18 is very small in comparison to r, and may be neglected in subsequent or substituting modulus value for x minus x prime in the denominator of equation 17. In equation 17, in the denominator, we have mentioned that it is x modulus x minus x prime. Now, from this argument, the x prime is very small, so that in the denominator, modulus x minus x prime, where we can drop x prime, and we can just write modulus x. And from equation number 18, modulus x is nothing but equal to, approximately equal to r. So we can write it only r in equation number 17 in the denominator. So in that case, one can modify that exponential e to the power I k modulus x minus x prime in equation 17 can be represented into approximately equal to e to the power I k r using equation number 18 exponential minus I x prime dot k, that is in the numerator. In the denominator, we can write only x, because we can write that x is very, very larger than x prime, and x is approximately equal to r. So in the denominator, we can write simply r. So the absolute value of x prime k is important, though it is very small relative to kr. So that is named as equation number 19. Now, using the same thing, we have modified this equation, and we have, by using equation number 18 in equation 17, to obtain the asymptotic. So ux is equal to e to the power ikz minus e to the power ikr divided by minus 4 pi r. That is, the denominator is represented by r instead of modulus x minus x prime, because x prime is very small. So it is simply x, and x is approximately equal to r. So therefore, we have represented denominator in equation number 17 as r, and the numerator is e to the power ikr minus e to the power I k dot x prime ux prime small ux prime d tau prime. So we have used equation number 18, equation number 19 in equation 17. So equation 17 is modified in this particular form. Comparing with the asymptotic condition we have obtained in the wave mechanical approach of scattering, one can find that f theta phi is equal to minus 1 upon 4 pi e to the power minus I k dot x prime ux small ux d tau, because we have removed the dummy variables, is equal to minus m divided by 4 pi h squared integral e to the power I k dot x prime bx ux d tau. Again, we have removed the dummy variable, and we have used equation number 9 for capital Ux. So capital Ux is equal to mvx divided by h cut square. And this is the formulation for f theta phi. For further reading, we recommend that Quantum Mechanics by Matthews and Venkatesan. Now we come to the applications of Green's function. That the general applications of Green's function in different fields. It is used in physics, especially in quantum field theory, aerodynamics, aeronautics, aeroacoustics, electrodynamics, seismology, statistical field theory. In quantum field theory, Green's functions take the roles of propagators. In scattering theory, it is used to convert Schrodinger equation into integral form, and that we have already represented in this particular our lecture. This is the painting of George Green, British mathematician. He was born in 1793 and died in 1841. His contribution is well known in mathematics as well as in physics. Now we come to last slide. And this is the picture of beautiful flowers blossom in university campus. You can find varieties of colors, pink color, red color, saffron color, orange color, and gulmohar and garmala trees. They are blossoming in a full bloom. And this is our department picture. Thank you so much for patient hearing. Now I stop sharing slide. Thank you very much. Thank you so much. Thank you very much.